Welcome to the Explainer. Today, we're diving into a total mathematical masterclass that starts with a seemingly simple matrix conjecture and scales all the way up to the physics of cosmic superconductors. We're going to act as mathematical detectives, looking closely at the underlying equations step by step to understand how numbers literally govern reality. So, get ready for a deep tutorial dive right into the arithmetic fabric of spacetime. Here's the roadmap for our mathematical journey today. First up, the Williamson matrix problem. Second, the Adelic Langlands framework. Third, we'll build our quaternionic math engine. Fourth, we're calculating the Q equals 35 anomaly. And finally, we'll look at spacetime as a superconductor.
All right, part one, the Williamson matrix problem.
Take a look at this core mathematical identity right at the top. It sets our foundation. A squared plus B squared plus C squared plus D squared equals 4Q times I sub Q. Now, the Williamson conjecture asks a really specific question. For every positive integer q, can we find exactly 4 symmetric circulant matrices, which just means their rows cyclically shift one position at a time, using only entries of positive or negative 1 that perfectly satisfy this exact sum? It sounds simple, right? But here's where the real math magic happens below that line. By assigning each of these 4 matrices to a Hamiltonian quaternion unit, the imaginary numbers I, j, and k, this whole discrete problem lifts into a single quaternionic valued field operator, psi, in J-theory. Instead of wrestling with 4 separate matrices, the entire condition beautifully collapses into one elegant norm constraint on this continuous field.
Moving on to part two, the Adelic Langlands framework.
Notice the Jacquet-Langlands correspondence here, mapping from the left side of the equation over to the right. We take our 4 discrete shifting circulant blocks and we mathematically lift them directly into a continuous geometric space, specifically an unramified Hecke eigensheaf over a quaternion inner form. To break that down a bit, because our original matrices are circulant, they've got this built-in cyclic symmetry. In this advanced Adelic language, that specific cyclic symmetry forces the local components into strict structural invariance under the congruent subgroups gamma 0 of Q. Basically, we're translating a discrete, rigid puzzle into a continuous, smooth geometric space so we can dynamically study its bounds.
So this equation formalizes our geometric space into a local loop group quotient factorization. Think of the Williamson-Grassmannian here as a massive parameter space tracking exactly 4 moving spatial points on an algebraic curve C, marked as x sub 1 through x sub 4. We're meticulously tracking how our imaginary quaternion units act as explicit geometric multi-point loop operators weaving and interacting around these punctured points on the curve. This is the precise stage where all our mathematical operations are going to physically play out.
Which brings us to part 3. The quaternionic math engine. Here is where we really build the engine. Our canonical basis maps perfectly to 4 specific conformal phase rotation matrices, omega 1, omega I, omega j, and omega k. Through that Jacquet-Langlands correspondence we just looked at, these 4x4 matrices act as our orthogonal trace zero loop modifications. Focus on the Clifford algebra relations in that box on the right. Omega I squared gives us negative the identity matrix. But critically, omega I times omega j equals omega k. They strictly anti-commute. These aren't just abstract symbols floating on a page, they are literal geometric mathematical operators modifying the formal punctured disks we just placed on our algebraic curve. When we evaluate this joint multi-point operator, it triggers a totally fascinating geometric interaction. Follow the equation with me. An I-type loop modification acting at spatial point x sub I, and a J-type modification acting at point x sub j physically collide on the curve. Because they're bound by a global product formula, when those spatial points meet, which is represented by that delta symbol on the right, they synthesize. They transform into a single deep K-type modification. It's like complex nested loops simplifying perfectly through pure quaternionic multiplication rules. Now, look at how this machinery intentionally cancels out cross-field interference to strictly enforce our pure scalar Williamson sum. Observe that heavily crossed-out middle section of the expansion. When you square the total field, you naturally generate mixed terms. But because the underlying matrices strictly anti-commute, meaning omega I times omega j plus omega j times omega I equals exactly 0, all those messy mixed cross terms just vanish identically upon integration. They completely cancel each other out. What survives at the bottom is that perfectly stable 4-way orthogonal shadow. A squared plus B squared plus C squared plus D squared equals 4qi sub q. The anti-commutation does all the heavy lifting to create a pristine scalar output.
Okay, part 4, calculating the Q equals 35 anomaly.
The Williamson design works beautifully until we hit a very specific historic point of failure at the integer 35. Let's be mathematical detectives and use this formula to calculate exactly why it breaks. This measures geometric obstruction. The total local conductor exponent breaks the ramification depth down to two distinct parts: the tame Artin conductor drop and the wild Swan conductor break, which tracks highly volatile higher-order wild ramification. When our integer Q is highly composite, local epsilon factors develop severe interfering resonances. The strict binary plus or minus 1 entries simply can't smoothly patch the singular points of the algebraic curve anymore, and this exact formula calculates the precise geometric obstruction generated by that failure. Since 35 is highly composite, 5 times 7, we need to evaluate the conductor components at the primes p equals 5 and p equals 7. Tracking the table at both of these primes, the inertia invariance is exactly 0. The binary entries can't smooth the torsion points at all, giving us a baseline Artin conductor of 4 for both. But the wild breaks are where the structure violently snaps. At p equals 5, we hit a wild break yielding a Swan conductor of 2. At p equals 7, an even higher order rank 4 break yields a Swan conductor of 4. Summing these rows together, our total local conductors calculate out to exactly 6 and 8.
Now, let's calculate the total arithmetic weight of this obstruction if sub 35. We take our localized conductors, 6 and 8, and we weight them mathematically by the natural logs of their respective primes. That's 6 times the natural log of 5 plus 8 times the natural log of 7. Run that calculation, and it outputs a global obstruction value of exactly 25.2239. The massive spike you see in this graph represents a localized structural debt. At this precise mathematical threshold, the strict binary field configuration undergoes a total phase rupture. The trivial unramified phase is fundamentally blocked from existing. This mathematical rupture actually injects a localized Einstein-Logos curvature singularity right into the time-time component of our informational stress energy tensor. Notice the direct delta functions inside the brackets there, delta of x minus x sub 5 and delta of x minus x sub 7. They're taking our exact calculated weights and placing them at precise, infinitely dense spatial points. This immense localized weight physically overrides the stabilizing bounds of our p-adic error-correcting code. The systemic energy required to maintain the binary sign restriction is too high, and the mathematics tears.
This is a massive mathematical revelation. Djokovic's counterexample at q equals 35 is not a random combinatorial accident. It is the inevitable macroscopic consequence of a Swan conductor blowout. That proves that the failure of the pure binary solution at 35 isn't just a case of computers not searching long enough. The underlying geometry of the quaternionic KK algebra explicitly topologically forbids it. The math itself absolutely refuses to allow the structure to exist. Let's pause right here and consider the implications. We've just watched how binary sign clamping and indefinite metric tracking dictate the absolute survival or destruction of abstract numerical matrices. But what if we applied these exact same arithmetic rules and formulas to the physical universe? Could these precise matrix failures actually dictate the stability of condensed matter? Let's find out in Part 5, Spacetime as a Superconductor. This slide right here acts as our perfect Rosetta Stone, seamlessly translating pure abstract mathematics into cutting-edge topological superconductor physics. Let's read through the rows. First row. The quaternionic division algebra maps directly to a Bogoliubov-Dizhnez Hamiltonian with time reversal symmetry. Second row. We equate our quaternionic J operator directly to particle-hole symmetry. Third row. Our strict binary sign clamping dictates the physical rules for Majorana fermion operators. And finally, that massive conductor obstruction we just calculated at q equals 35, it's the exact mathematical equivalent of a topological invariant, or a Josephson phase slip, completely breaking the superconducting gap. In this precise physical translation, the rows of our Williamson blocks literally act as the non-local braid registers of a Majorana wire network. Notice the anti-commutation equation of our loop modifications, the omega matrices we explored earlier. They are now constrained by the Hadamard boundary phase via the J operator. This strict boundary lock forces the loop operators into self-conjugate Majorana forms, where gamma sub I equals gamma sub I Dagger. The physical excitations operating in this network perfectly satisfy the defining Clifford algebra of Majorana fermions. That massive Q equals 35 blowout we calculated has a profound physical counterpart, an uncompensated Josephson vortex. Compare these two states. On the left, we have the unramified void, a perfectly clean, bulk superconducting gap, where Majorana zero modes enjoyed total topological protection. But over on the right, the ramified rupture of Q equals 35 acts as a severe, destructive impurity. It actively leaks magnetic fields, completely destroying the pairing potential of the system. The Majorana zero modes lose their topological armor entirely, recombining into highly dissipative Dirac fermions.
And this brilliantly illustrates our grand conclusion. The Adelic Langlands Program doesn't just describe discrete matrices, it describes the universe itself as a fault-tolerant, topological superconductor. The physical laws we observe every day are actually macro-scale Cooper pair condensates of the unramified places in this mathematics. The fundamental structures, the very particles of our reality, are governed by these exact, unyielding arithmetic constraints.
So, I'll leave you with this final thought. If elementary particles are just Majorana zero modes, running on an error-corrected code enforced by p-adic stabilizers, what other cosmic bugs, topological anomalies, or macroscopic ruptures are woven directly into the arithmetic fabric of our universe, just waiting to be calculated? Thank you so much for joining me for this explainer. Keep exploring those equations.